Here, I'll explain the usage of the Hess law, one of the principles in thermodynamics, to find out the enthalpy change of the theoretical reaction that could not happen easily. For example, if we want to calculate the heat formation of acetylene, which is C2H2 gas, from its element, using the most stable format of the carbon, which is graphite, and the most stable format of hydrogen, we construct this reaction that carbon from the graphite react with hydrogen to form acetylene. The enthalpy change of this reaction is actually the heat formation of acetylene. However, the problem is, in reality, it is very hard to make graphite directly react with hydrogen to form acetylene. So how can we accurately obtain the change of the enthalpy of these reactions? So the chemist doing through the following steps. Okay, so instead of have the reaction between graphite and hydrogen, we can easily burn graphite in oxygen, and fully reaction give us carbon dioxide. It happened to be that the enthalpy change of this reaction from graphite, oxygen to carbon dioxide, this is the heat formation of the enthalpy for carbon dioxide. Why is that? We have one more of carbon dioxide here, and we generate one more of carbon dioxide from the pure element carbon in its most stable format, graphite, and pure oxygen in its most stable states, oxygen 2. And we can measure the heat of this process in constant pressure. That gives us the enthalpy change. In this case, the enthalpy change of this reaction is the heat of formation of carbon dioxide. It is negative 393.4 kilojoule. It tells us this is very exothermic reactions. On the other hand, we can also burn hydrogen. Hydrogen is one of the reactants here. We can burn hydrogen in oxygen to get water. It happens to be the enthalpy change of this reaction is the heat formation of water. Why is that? Because this reaction, we formed water from the pure element hydrogen in its most stable format, H2 molecule, and the most stable format of the pure oxygen element, that is O2 molecule, and we form one more of water. And this reaction is also very exothermic, with delta H as negative 285.8 kilojoule. And thirdly, we can also burn the acetylene gas, which give a lot of heat. The burning of the acetylene gas in oxygen gives us carbon dioxide and waters, and this is a balanced burning reactions of acetylene in oxygen give carbon dioxide and oxygen, and the enthalpy change of this reaction is very, very negative. So this is very exothermic reactions. Okay, now let's recap. So our target reaction is 2 carbon in graphite react with hydrogen to produce one more of acetylene, C2H2. So we need carbon, we need hydrogen, we need acetylene, nothing else. And we found that we have a carbon in form of graphite in this place, and we have hydrogen, H2, in this place, and we have acetylene in this place, and we also have oxygen, carbon dioxide, oxygen, water, oxygen, carbon dioxide, and water. We'll try to get rid of all of this molecule. But how? First, we see we have carbon and hydrogen on the left-hand side of the reactions, and carbon, hydrogen also on the left-hand side of reactions, but acetylene is on the right-hand side of the reactions. But in these reactions, acetylene, C2H2, is on the left-hand side of the reactions. So to make this molecule appear on the right-hand side, we need to swap or flip these reactions. When we do the flip of these reactions, we need to change the sign of the delta H for these reactions. Here we are. You can see that we already, in this slide, we flip these reactions, move the previous reactant to the product side, and move the previous product to the reactant side. And very importantly, we change the sign of the enthalpy of these reactions. Now delta H is very positive. This reaction is endothermic reactions. Okay, now we have acetylene at product side. Okay, so, and we check others. We have carbon, hydrogen, we have acetylene, and we don't want oxygen, and we have oxygen on the as a product, and as a reactant, and as product. We also have carbon dioxide as the product, but carbon dioxide as reactant, water as a product, and water as reactant. Now what we'll do next? Let's recap. We want to have carbon as the reactant, hydrogen as the reactant, acetylene as the product. And we have a carbon as a reactant, hydrogen as a reactant, acetylene as a product. But we want to get rid of oxygen, and carbon dioxide, water, and water. To cancel those molecules, let's see what we can do for each of them. First, let's focus on carbon dioxide. We have 4 carbon dioxide as a reactant here, 1 carbon dioxide as a product here, nothing else. So therefore, we multiply these reactions by 4. Also, we need to multiply the change of the enthalpy by 4. We have 2 water molecule here, 1 water here. So therefore, we multiply these reactions by 2. Also multiply this enthalpy change by 2. Then this gives us these reactions. Okay, we have 4 carbon dioxide. Here is the enthalpy change of these reactions, 2 water molecules, and this is enthalpy change of these reactions. Can we cancel these molecules we don't want? Let's see. 4 carbon dioxide, 4 carbon dioxide. Yes. 2 water molecule, 2 water molecules. 4 oxygen plus 1 oxygen is 5 oxygen, and this is 5 oxygens. Yes, we can. So therefore, we need to sum the reaction 1, 2, and 3. We sum this reaction together, and meanwhile, we need to sum these 3 enthalpy of the reactions. Okay, so just like the mass, we sum the reactions, we sum the enthalpy change. So after that, and we cancel these molecules. Okay, right here, water. This. Okay, 4 carbon as graphite come from here, 2 hydrogen molecules come from here, and 2 acetylene molecules come from here. And sum of these 3 enthalpy give us the enthalpy of these given reactions, 453.2 kilojoule, positive. So therefore, this reaction is endothermic. But our target reaction is 2 carbon with 1 hydrogen produce 1 mole of carbon acetylene, C2H2. But we have 2 acetylene. So therefore, we need to divide this reaction by 2. And what do we do to the enthalpy? Yes, we divide it by 2. Give us 2 carbon as graphite, react with 1 hydrogen molecule to produce 1 mole of acetylene, and delta H is 226.6 kilojoule. By definition, this is a heat, this is the formation of enthalpy of acetylene, because we formed 1 mole of acetylene from the pure carbon in its most stable format, which is graphite, and hydrogen elements in the most stable state, that is hydrogen molecules. Okay, this is quite powerful technique because we cannot make this target reaction happens, but through 3 separate reactions: burning of the carbon, burning of the hydrogen, burning of the acetylene, which can be easily measured accurately. I mean, the heat of these reactions can be easily measured, and use these 3 reactions, we can obtain the target reaction, the change of the enthalpy of the target reaction very accurately. So similarly, here is another examples. So what is the heat of the formation of carbon monoxide? To get carbon monoxide, CO, by definition, we need to combine the pure element of pure carbon element in its most stable format, which is graphite, and oxygen element is in its most stable pure oxygen element in its most stable format, which is O2. Yes, it seems like we can burn carbon in oxygen to get carbon monoxide, but the problem is extremely hard. It is extremely hard to control the reaction from carbon burning oxygen stop at carbon monoxide without producing any carbon dioxide. So actually, if you burn it, most of the product is carbon dioxide. So how can we get this? So people are clever. They think about these ways. Okay, yes, I can burn graphite in oxygen to get carbon dioxide. That can be easily done. I can also get carbon monoxide. So people burn carbon monoxide in oxygen. Yes, we can burn that. Also to get carbon dioxide. Okay, both reactions are very exothermic. So now, can you do the trick from these 2 reactions to get the target reactions? Yeah, let's try. Here we are. The target is graphite react with oxygen to get carbon monoxide. So carbon monoxide is a product. So we make rearrangement that we have a carbon dioxide dissociating to carbon monoxide with oxygen is actually flip of these burning reactions. Actually, it's flip of the burning reaction of carbon monoxide in oxygen, and we keep the same order as the carbon graphite burning oxygen to get carbon dioxide. So if we sum these 2 reactions, we can see we can cancel carbon dioxide and cancel the half of the oxygen molecules. As of course, we need to sum the enthalpy of these 2 reactions. As a result, we have a graphite react with half of the oxygen molecule to produce, or actually 1 mole of graphite to react with half mole of oxygen to get 1 mole of carbon monoxide. By definition, the enthalpy change of this reaction is the formation of the enthalpy of carbon monoxide, which is negative 110.5 kilojoule per mole. So here is a slide to show the overall process. that if you burn carbon graphite in oxygen, it can all the way through to the carbon dioxide. Or it's hard to do, but it's theoretically we can get halfway to produce carbon monoxide. We can also burn carbon monoxide in oxygen to get carbon dioxide. So to get this part, we get this part and this part. The differences is what we want. So that's based on the Hess law in thermodynamics. Okay, I hope this is clear enough, and thank you for watching.